So delving directly then into the first of our types of metamorphism, contact metamorphism, we're going to look at what metamorphic rocks do under a an elevated temperature, but not necessarily elevated pressure regime. So remember that we're talking about an intrusive event or some other extreme heat bringing event happening. So we've got, I'm going to illustrate it with sedimentary strata here, but you could do this with igneous. It just gets a little more complex, or with remetamorphosing metamorphic rock, because then you got to try to keep up with, well, what is it going to change and what is it not. So we'll just start from the simpler sedimentary version. So we're looking at limestones here on the bottom, and I've got a sandstone drawn in here, and then a shale, and we're going to take those apart one at a time. This is our big pluton coming in here as a molten magma, and so it's bringing lots and lots of heat with it. So we're going to change where we are on phase diagrams, and we're going to recrystallize some of these minerals involved. And so it turns out that what happens is a lot related to what you start with. So we're going to look at the three different packages here separately, and so we're going to start looking at the shale and what might happen to the minerals in this shale body up top as they are coming into contact with all this heat. And the differences are going to arise from the starting mineralogy in what's called the protolith. Protolith means starting rock. So the rock that we start with, and in this first case, that's going to be a shale. Okay, so, well, interestingly, my image sources here are here before the images. Well, okay, they'll just work with me on this. All right, so a shale. What is a shale? So you guys identified it in the sedimentary rocks lab. It was that fissile materials, aphanitic, you can't see the individual crystals, and it's typified by clay-sized particles, maybe silt-sized particles, but also by clay minerals, which are your phyllosilicates usually. And remember, we call them silicates, but often aluminum is involved, and so you could also call them aluminosilicates. All right, so we have this bed down here at the bottom of phyllosilicates or phylloaluminosilicates, and we're going to intrude. Oh, well, so what is it made of? I guess I started from the idea of what is it made of. So this represents a phyllosilicate here with, these are my sheets, my phyllosilicate tetrahedral sheets. They have an octahedral layer in between, so they're TOT. But so these are those sheets that we were peeling off of the micas, and in between are these cation sites. But now let's use an analogy of making pottery here. So let's think about the clay that you would use to make pottery, and one of the ones that makes good pottery is called smectite. Smectite has these phyllosilicate layers, and in between are cations surrounded by what I've drawn here are water molecules surrounding my cations. So these sheets are a long, long way apart because of all the water hydrating the cations in the middle, in between the sheets. But now thinking about our pottery, what are we going to do to it? We're going to form it into, like, mold it into a vase or whatever you make out of your pottery stuff, right? And then you're going to stick it in an oven, and you're going to bake away that water, and that's going to change what that mineralogy looks like when you do it. Well, we're going to intrude our shale unit with this really, really hot magma. That's just like sticking your vase in that oven, in that pottery furnace. We're gonna heat it up, right? And we're talking about extreme temperatures, remember. So this thing might be a 1200 C magma, right? And so you're gonna have zones maybe not very far from where it actually contacts the rock. You're gonna get down to like 800 and 500 C and back to so maybe our starting was already buried deeply and we're at like 200 C, but our smectites might still be okay at that. But if we start baking them, what's going to happen to those water spheres? The water is going to start to dehydrate or come off of, and leave non-hydrated stuff in between. Now, for future reference, I am going to make a note to myself here that I'm being very, very loose with the chemistry and the mineralogy here, and what can transition to what. That would have to be cleaned up in an upper level course, but I think it'll be fine for our 1121 course here. So let's look at as if we are losing the water shell around the cations in between. And so we'll start to collapse. We'll collapse that structure. See, it's much, much closer together. This sheet up here and this sheet down here are much closer. You can have a brucite structure where we've got another octahedral site in between that shows magnesium. You could have aluminums in there. You could have even irons in there occasionally. But in a chlorite structure, you usually think of it in terms of magnesium. Or we could have little bitty muscovites. Sometimes we call these illites. They're isostructural with muscovite a lot of the time. A little bit agnostic on what cation goes in between here. This diagram shows potassium. We could also show an iron in there and be more like a biotite. But so what happens is the water has been driven off of the red cation that I showed originally, and collapses down the whole sheet structure. So you can also see that you have a denser material. Well, think about our pottery kiln, right? Our furnace that we stuck that vase in. As you're baking away the waters involved in those structures, you're getting a tighter, harder structure. It's also a bit more dense, and that's happening as our magma here bakes our shale. Well, can we go even further than where we are now, just baking out the water shell and collapsing those structures? Yes, actually we can. If you keep going far enough, you can actually change the structure. You can still see that the tetrahedra are around, but they've been squashed down, and now there's some other octahedral sites at different orientations. This is a garnet structure, so you can actually transform your clays, and garnets will start popping out they'll start growing in the matrix because of the heat that you put it under. So much temperature that the stability, the minerals start to shift actual chemistry. And so a garnet chemistry is actually different than a phyllosilicate, but definitely the structural difference, the mineralogy difference. So all this happens, and I guess there's another phase that you get to with our analogy of the pottery, and you get eventually to porcelain, and you're starting to see a change in the actual chemistry then, more than just driving off water. You're actually starting to change some of the sheet structure into a more tectosilicate structure when you go to a porcelain. All right, well, let's shift our attention then to that next layer down from the shales, and let's look at the sandstones. Now, remember that what happens is going to be really, really dependent on what our protolith, our starting rock, is. And we had a lot of stuff going on with this shale, right, with the aluminophyllosilicates. Well, if we start from a sandstone, right, what's a sandstone made of? It could be a lot of things, mostly your sand grains, but the most typical mineral composition is just quartz. All right, so we're going to consider our sandstone here to be a quartz sandstone, an arenite, and we're going to look at what happens in that contact metamorphism zone for it. Remember that we need recrystallization to call something metamorphosis. But they don't have to change to a different mineral when they recrystallize. They can recrystallize to the same mineral again, and that's what our quartz is going to do, right? So we've got our intrusion, and we've got our different temperature zones, right? But this guy, let's just say, is nice, happy quartz crystals. Now, quartz is a tectosilicate. It's a really, really strong structure, and it's a really stable structure. So if you change that temperature, now eventually you could melt quartz, but it takes a really high temperature, and we're not going to get all the way there. We're just going to keep it solid, but we're going to try to metamorphose it. Well, turns out that quartz is still happy even at those elevated temperatures. Now, the quartz crystals themselves may undergo solid state diffusion and recrystallize. They have to have recrystallized in order for us to call this a metamorphic rock. But they've recrystallized from a quartz crystal to a new quartz crystal, still a quartz crystal. Even under some of the more extreme metamorphic conditions, quartz can still be one of our major stable phases, and just happy old quartz, it's almost always around. And then we'll shift to a discussion of what happens in my favorite, the limestones. So let's see, what are limestones made of? Well, let's keep it simple and just consider our limestone to be completely made of calcite. All right, so let's think about calcite and its stability and how it may recrystallize. Now remember that we're dissecting this under not much changes in pressure. So we're going to be looking at a situation similar to the quartz where the calcite is just going to be stable across the entire field here. So we've got our magmatic intrusion. We've got our different temperature zones. But remember, we're not changing pressure very much because this is contact metamorphism, right? So instead of the actual crystal version I did with the sandstones, let's look at the rock here. So we're starting from a nice limestone here, right? And it's all calcium carbonate. But remember, these are grains, and maybe they've got fossils in it. They've got some void spaces. They might have oolites, various structures that I loved so much when we were talking about the sedimentary rocks, right? But then we recrystallize it. And we can recrystallize a limestone into a marble. Now, let's see, we said limestone was made all of calcium carbonate. Well, so is marble. It's all calcite also. But you don't see any of those original structures. In this version that I picked out here, you might see a hint of original compositional layering right there in the middle. But those can be really misleading when you get to metamorphic rocks. So here we've just got generally recrystallized massive marble. So that happens again like it did with the quartz, is we just recrystallize it into a new version of the same mineral, or a new iteration of the same mineral. We can do that even with the most extreme of metamorphism. We get a marble. Now notice that especially in the case of the marbles and the quartzites, we have a non-foliated rock here. When we talk about classifications of rocks, we'll talk about foliated versus non-foliated. These are all non-foliated. Now, in the case of a limestone to a marble, there's really no way to foliate calcite. With our aluminosilicates, though, those could have been very, very well aligned. And in the case of contact metamorphism, they're often not. They're just kind of randomly aligned micas and stuff growing in them because we don't have any clear direction of pressure in this. And so you get just a non-foliated bulk rock with really, really big crystals sometimes. Okay, so contact metamorphism. Now, put back my diagrams here to talk about where we're at. So remember that we have had a temperature change, but we didn't get much pressure. So we looked at this zone right here of contact metamorphism where we're talking about a temperature gradient without going very much on the y-axis where the pressure is. And if we look at this other with the metamorphic facies, so we're starting out up here and we're starting to shift through this Hornfels metamorphic facies. I guess we could get all the way into the granulite if we tried hard enough, but we're probably going to melt some of those right where they're touching the magma before we actually get into a granulite facies because we don't have enough pressure to keep them solid. All right, so that's contact metamorphism, and next time we will delve into regional metamorphism.